Well, time to get started, I guess. I do want to point out that we have. Wait, this is really human. Okay, hopefully you can hear me online now. If you have questions online, I think you can probably take your mute off briefly and ask me a question, and I can hear you here if you want to ask a question. I should mention, first of all, we have our exam next time, just during the regular class hour. I'll send it out right at the beginning of the usual class time. And you have an hour and 15 minutes to run it off and email it back to me. So it's by email, just like before. Don't come to class, right? Not in person. Most problems similar to the practice set on Canvas. Make sure you look at the practice problems. That's the most important list to look at probably for being similar to the test. Oh, similar practice set. The practice set is much too long. I'll try and make the test slightly shorter than last time. They'll all be similar to homework, but I might ask some homework that's not on the practice sheet. Okay, any questions on the exam? Oh, important question. It's open book, right? Open book and notes, just like last time. It's too tempting to look anyway. But no help from any persons, no online tutors, no communicating with your classmates during the test. Open book notes, but no help from people. I had a test like that I was taking as a graduate student for my preliminary exams. You don't get through the program until you pass this barrage of exams. If you fail them once, you get one more chance, and then you're out of the program. Once passed the first time, you don't go with that stress the second time. And boy, I was stuck in this stupid physics problem. But fortunately, the professor made an open book, and I was fortunate enough to find it in the book. So I appreciate open book when it's available. Use your booklet where you need to. Um, all right. Oops, I just erased what I needed to. Uh, recall, here was the last problem we wanted to do last time. I didn't quite get to it. It's the last thing on the homework that's due tonight, so I want to make sure I looked at this. Maybe you've already done it. Recall that a level surface, I have to, all that work, I have to rewrite it now. Again, I guess. A level surface expressed as the form f of x, y, z equals k. And at first you say, wait a minute, didn't we make surfaces z equals f of x, y? Well, you can. Uh, but also a lot of surfaces are generated by f of x, y, z equals k, like the ellipsoid, right? X squared over a squared plus y squared over b squared plus z squared over c squared here equals 1 over here was the standard equation for ellipsoid, for instance. And what you can do, if this is locally differentiable, locally meaning like you have the ellipsoid there, along the edges where you got a vertical tangent, it's not differentiable because it's infinite slope. But if you break it up into two pieces, you can take the top half and the bottom half, except for the boundary there with infinite slope, and take a piece of it or the whole thing and say, oh, it has a nice derivative all through there, right? You can, if you can actually solve for z as a function of x and y and see it if you want. But even if you don't do that, if it's locally differentiable as thinking of z as a function of x and y, even if you can't actually solve for z, uh, a lot of these surfaces, actually from something called the implicit function theorem, that there's some z can be written as a function of x and y, and if that's differentiable, then you can apply the following rule, the chain rule we use to prove that this has tangent slopes. Never erased my ellipsoid either, probably. All right, I might think of this in XYZ space. And if I think of some portion of this where C is actually a function of X and Y that's differentiable, I might say, well, at this point in the XY plane, I wonder what the slope is in the X direction, right? dz dx. I wonder what the slope in the Y direction is. Slope is dz dy. You can calculate them with these formulas, right? dz dx is minus fx over fc. dz dy is minus fy over fc. We derived that using the chain rule last time. Let's do one short example, and then the rest of the time we'll spend on review problems. Since this is a review problem, I could ask you this one. This is one out of the homework that I thought would be worth doing. Well, I gave you xz squared plus y to the ninth z plus 8xy minus 1 equals 0. So you can make this your f of x, y, z, right? I have no idea what surface this generates, right? It's got y to the ninth power. What does that do? I don't know. But I can still calculate the slope of the tangent line of this surface as follows, right? Suppose I say find, we'll just do the first one there, dz dx. Oh, actually, this should be not 1. Let's make that 10. Forgot to fix that. Equals 0. I changed the problem a little bit. Let's find dz dx at the point 1, 1, 1. This makes easier algebra, right? You first have to make sure this is actually on the surface, right? So you plug it in. 1 plus 1 plus 8 minus 10. Sure enough, it's 0. So this is a point on the surface. And given that it's a point on the surface, I can now use these formulas to calculate partial derivatives, slopes of tangent lines to whatever surface this is. So this one means take the derivative of f thought as a function of x, y, and z. So fx means partial derivative of f thought of as a function of x, y, and z, all the independent with respect to x. So what have I got here? Minus dz dx at an arbitrary point x, y, z. I just first look for partial of f with respect to x. Here's my capital F, I guess I should call it to be consistent. Partial with respect to x gives me z squared plus 0 plus 8y plus 0, right? Treating y and z as constants, right? Derivative of xz squared is just z squared. Derivative of y to the ninth z is 0 because these are both constant. And then partial of f with respect to z, treating x and y as constant. I get x times 2z plus y to the ninth. But good thing I didn't pick a big number and have to take it to the ninth, huh? Plus nothing, plus nothing. So there it is, minus partial of f with respect to x over partial of f with respect to z. Right? And now I just plug in, if I want this at 1, 1, 1, I'll just plug in 1 for each of the variables. And I get 1 plus 8 is 9. That's 1 plus 8. 2 plus 1, I get 9/3. I get 3. So the slope of the tangent line in the x direction is actually equal to 3, even though I have no clue how to draw the surface. How about that? I don't. You could technically solve for z as a function of x and y using the quadratic formula, but you get a terrible mess. Trying to take the derivative would be much harder than this. So this is a real convenient way to do this without, you know. Can you imagine if you solve this with a quadratic formula, get z a complicated function of the square root? of x and y in there. If this is much easier. The drawback is that you have to, in general, uh, know the values of all 3-point variables. You don't just say at the point x, y, you have to say at the point x, y, z to plug it in. This is called implicit differentiation. Because you don't solve for z explicitly as a function of x and y and take the partial derivative, you instead just take the partial derivative of each side with respect to x of this equation and come up with is effectively what it's doing. Proof what did that. And so the result is you have to plug in all of x, y, and z, not just the point x, y, what you want the tangent. Maybe I should put an analogy just to show, because I think it's worth understanding what you're doing when you get out. That's what you have to get from math class. In the other classes, you get the formulas a lot of times. But if you don't know the theory behind it, you'd be like me in my graduate school taking physics. When can I use this formula? I could never figure it out. It's, uh, you know, except I take my math class and then I'd figure out, oh, that's what it's for. But like this, remember the analogy to calculus 1. Uh, if you had some equation where y wasn't given explicitly as a function of x, like x squared plus y squared equals 1, there's the unit circle. Suppose I wanted to find the slope of the tangent line at some point on the unit circle without solving for y. On this one, I actually can solve for y, right? Y is plus or minus square root 1 minus x squared. But see, this is a circle. Y is not a function of x, but you can still find the slope of the tangent line either by solving for y in the top half, y equals square root 1 minus x squared, and y equals minus square root 1 minus x squared in the bottom half, and taking the derivative directly, explicit integration we call that. Or we can take the derivative with respect to each side, treating y as a function of x, just like up here we thought of z as a function of x and y. We think of this one, y a function of x. We take the derivative of each side, treating y as a function of x, and the derivative is 2x for this one, plus derivative of y squared by the chain rule, right? It's dy squared dx is dy squared dy dx by the chain rule, right? Equals derivative of 1 is 0. And so what you got is 2x plus 2y dy dx equals 0. And you can subtract 2x and divide by 2y and get dy dx is minus x over y. And so now if you want to find this, say, at the point whatever, 1/2 square root 3 over 2 in the unit circle, you can just plug in both coordinates. Let's say this implicit differentiation give you the slope as a function of both x and y, since you didn't explicitly just differentiate the function. So you have to plug in both coordinates as the drawback. So now I say dy dx at the point 1/2 square root 3 over 2 is just gotten by minus 1/2 over square root 3 over 2 is minus 1 over square root 3. So I know that's the slope over here at this point, 1/2 square root 3 over 2. And I never actually had to write y as a function of x and take the derivative, right? I just took the derivative of the equation, and that worked. So that's implicit differentiation. And that's what we did just now. If we thought of f as a function of 3 variables, x and y, and z is a dependent variable function of x and y, we took the partial derivative of this and found out that we got that great formula that dz dx is minus fx over fz. The formula, and so this is doing this without writing this by formula. Treating 2 variables as independent, the third one is dependent, and taking the derivative of the equation f of x, y, z equals k on both sides. So that's what that was, implicit differentiation. It's supposed to be an analogy to this. When you can't solve an equation explicitly for z, you can sometimes still find the slope of the tangent line with this implicit differentiation formula. Any questions on that? Hope that wasn't too long. That'll help you do the last problem on yours. It's like one of them is just that one at a different point. All right, now, anything that's been bugging you? Have you been trying the problem, seeing if you think things that are difficult? I'll pick a few of these. I'm going to do a problem with chain rule. I thought this is kind of a good one to go over. If you look at 1B, oh, and by the way, I'm deleting one of the problems on the thing. It's we did it in class and the recording didn't come out and there's no homework in that section. I thought, boy, I better not do this. I started looking at this earlier this morning. Um, delete 2G. I've already done that online. This is on the old uh, practice set. To find where you find A equals ATT plus ANN. This is a real important problem actually in physical sciences, but we just haven't had time to do it. So that won't be on there. I mean, we went through it, but I didn't have any homework on it yet. I don't want to give it this close to the exam. I've already online replaced it. So if you load down, this is already fixed online. The new 2G you do want to do it was 2H. On Canvas, 2G is the old 2H. Do it. All right. That'll save you from frustration trying to do a hard one that I won't put on there for this. Maybe we'll get a chance to talk about that again. Let's look at 1B then. Let's use the chain rule to find the G to U, partial of G with respect to U, if G is actually a function of xy, is x squared minus y squared, and x and y are in turn these functions of U and V. Okay? Uh, So what do? The idea is you could just plug these in and get the right answer, but if you do that, it'll give you 0, y, close to 0. Then use the chain rule. When I say chain rule, emphasize that, make sure you write the chain rule. What you want to do is write this down, because you can get it by plugging in, but the idea is I don't want to ask some theoretical junk that's you can't do the other way. It's too hard a problem for a test. You write the chain rule that dg, du, g thought of as a function of u and v through x and y, like this, right? G is originally a function of x and y and creates some surface, z equals g of xy. But then x and y are in turn functions of u and v, and if you rewrite it that way, then in u, v, g, z space, you can write the surface z equals g of x of uv, y of uv, and some surface. And you can take the slope of the tangent line at some point uv down here, in the y in the v direction and in the x u direction and v direction. Those are the partial derivatives, right? dz du is for that slope, and dz dv for the other one. That's the idea. If it's a function of a function of more than zeros, you can use this chain rule then. I'm going to erase this. I forgot parenthesis too. Um, what is dg du? Thought of as a function of u and v through x and y. The rule says you take dg dx dx du chaining through x to u plus dg dy dy du. And you can write that down without the picture. I think when you're first learning this, the picture is really nice. Book doesn't bother to put it because you don't have to have it. But g is a function of x and y, which are in turn functions of u and v, right? And you can imagine all the partial derivatives on here. You don't have to write them. G to x gets dg dx, x to v gets dx dv, and so forth. Dx du goes from x to u, dg dy. So you don't have to write all these out, but you can figure them. All right. And what you do is you're taking, when you want dg to u, you take all paths from g down to u, which are these two, and multiply the partial derivatives on each path and add them, right? So, but it's really just chaining through each variable to u. dg dx, chain through x to u, and then chain through y to u, right? And add them all together. So you can write out the picture if you want, but once you figure this out, you don't have to. Now, what is dg dx? It's easy, right? X squared minus y squared partial derivative is 2x minus 0, since you're treating y as a constant. Dx du, taking partial derivative of this function with respect to u, well, derivative of e to the u is just e to the u, and cosine v is treated as a constant, since v is a constant, right? Just cosine of a constant is a constant. So this is e to the u, cosine v is the derivative of e to the u times this constant cosine v. And then dg dy, derivative of x squared minus y squared is 0 minus 2y, multiplying dy du. Well, why is this function? The derivative of e to the u is e to the u multiplying this constant sine v. Just get e to the u sine v. This actually has a real neat connotation, which I haven't really mentioned to this point, but this is used quite extensively in coordinate changes. I mean, suppose x, instead of being e to the u cosine v, was r cosine theta, and y was r sine theta. You can take partial derivative of g with respect to r, partial derivative of g with respect to theta, partial derivatives with respect to polar coordinates by just using these things. This is actually a coordinate transformation to another coordinate system where x is equal to e to the u cosine v, y is e to the u sine v. This is like a coordinate transformation. You find the slopes of the tangent lines in the other coordinates. So it's pretty neat what you can do with this. All right, now this is not finished. Why am I taking off points in your test for writing an answer? Not much, but a little. Yeah, you want to leave the final answer in terms of u and v because you're thinking when you write this of g as a function of u and v through the intermediate variables x and y. You want to write the slope of the tangent line in terms of u and v only, right? Since you're taking the partial derivative at the point uv. There's the slope is dg du, right? So I'm going to write x is e to the u cosine v. So this is 2 e to the u cosine v times this e to the u cosine v. And then minus 2y is minus 2 e to the u sine v. And then times e to the u sine v. And there it is. There is the whole thing. I'd still like you to clean that up a little bit. Right? You get down here, you want to simplify. So an e to the u times e to the u is e to the 2u. And I factor that times 2 out of everything. I said this is 2e to the 2u multiplies everything. Times cosine squared v minus sine squared v. That's much simpler. But once this thing gets hung up, I can never keep on writing. All right. Um, all right. So here's what you wind up with. This is okay. I would accept that for an answer. It's kind of nice if you recognize the double angle identity from trigonometry and rewrite this as e to the 2u times cosine 2v is cosine squared minus sine squared v. So that's the best answer. But this one's fine too. All right. Be able to do chain rules of all sorts, right? That's just an example. Nothing's really stuck. No. Okay. Any particular one? Here's 3B then. Well, a contour map of f of x, y, showing at least 4 level curves. Suppose f of x, y is x squared plus 4y squared. Draw contour plot of level curves. One of those geographic maps. It's great software for doing that these days. It's amazing. Um, all right, so for this one, uh, be happy on this one. There's no actual calculus in it. What you do is you set f equal to different numbers that make it easy. For instance, if I put f of x, y equals 0, right? Put k equals 0. Level curves are f of x, y equal a constant k. Well, suppose I put k equals 0, then I've got 0 equals x squared plus 4y squared. I'd like you to figure out that that means equivalently x squared. Since this is non-negative and this is non-negative, the only way to make that equal to 0 is make these both 0, which means that x squared equals 0 and 4y squared equals 0. You only have one solution of 0.00. If, on the other hand, I put k equals 1, then I get 1 equals x squared plus 4y squared. And I want to recognize what kind of curve that is. What is it? Write it more suggestively. X squared over 1 squared is x squared plus y squared over a half squared. A half squared is 1/4, and 1 over a fourth is 4. That's that one. Equals 1. Oh, it's an ellipse, right? X squared over a squared plus y squared over b squared equals 1. It's an ellipse that I can sketch with a equals 1, the semi-major axis, and b equals a half, the semi-minor axis, in the y direction. So I'm throwing in a trick review of conic sections here. And here's how you can make your sketch of level curves. And you plot the origin and label it 0 for k equals 0. You plot an ellipse with semi-axis 1 in the x direction and half that in the y direction, about like this. 1 and 1. This is the k equals 1 level surface. Then pick a convenient number so you have an easy time sketching. Let's plot k equals 4. Now I've got 4 equals x squared plus 4y squared. Oops. Which means dividing by 4 and switching sides, I've got x squared over 4 plus y squared over 1, if you like, equals 1. That's again an ellipse, right? So I've got concentric ellipses, if you like. Now the semi-axes are 2 and 1, so I'm going to go out to 2 here and 1 here, and I'll sketch this one. Also goes back to -2, right? -1. I can do the k equals 4 level curve. And then I can try 4 different ones. I can't remember now. Yeah, 4 level curves. Let's do another easy one. Uh, k equals, how about 16? Then I get 16 equals x squared plus 4y squared, and I divide through by 16 and get x squared over 16 plus y squared over 4 equals 1. Evidently, my semi-axes are a 4 and b 2. I go up here to 2. Oops, 2. And out here to 4. And I can plot this big old ellipse, right? There's k equals 16. That's what I'm looking for. In this case, selection or possibly a point if you do the k equals 0 one. Um, suppose I look at 5a here, and I say f of xy is equal to x over the square root of y. Find the tangent plane at the point x equals -1, y equals 1. How about that? This one, it behooves you to have memorized some of this stuff, even though it's an open book test, or at least have your formula sitting in front of you, right? So you might write a formula sheet. Um, it's an analogy to a tangent line of calculus 1, right? And it just says this: z equals f at the point plus partial of f with respect to x at the point times x minus the x coordinate plus partial of f with respect to y at the point times y minus the y coordinate. That's the equation of the tangent plane. It's an analogy to calculus 1, where you just took the value of f plus the derivative times x minus x0. So there's the tangent plane equation just by formula. And now you need to take these partial derivatives. So partial of f with respect to x, since this is x times something treated as a constant, it's just a constant, 1 over square root y. Fy, if you think of this as x times y to the minus 1/2, it's an easier derivative than the quotient rule, is x times minus 1/2 x y to the minus 3/2. So it's minus 1/2 x y to the minus 3/2, so it'd be square root of y cubed. If I do a quick partial derivative, uh, there it is. Now you plug in the point -1, 1. Well, let's see, f of -1, 1 is -1 over 1. I guess I could write out -1 over square root 1 plus fx is 1 over square root y is 1 is square root 1 times this one at -1, 1 times x plus 1 plus fy, which is this one at -1, 1 uh, minus -1 over 2 square root of 1 cubed. First plugging in -1, 1 times y minus 1. It looks like -1 plus x plus 1 times 1 plus 1 over 2 y minus 1. Let's see, it's -1 cancels the plus 1. I've got x plus 1/2 y minus 1/2. There's the equation of the tangent plane. Z equals x plus 1/2 y minus 1/2. This is kind of a nice way to do it because you write z of x and y. Or you can put it into the standard form and call this x plus 1/2 y minus z equals 1/2. That would be good too. Put it in standard form. Either one of those is great. I would multiply this 2 by 2. We call it 2x plus y minus 2z equals 1. This would be better. Get rid of those fractions. Good. I hope 10 minutes. Okay. Suppose I ask you to take d dt, the derivative of a vector valued function, r of g of t. You know, I've changed, let's see. Yeah, all right, r of g of t, where r of t is 2 sine 2t minus 3 cosine 2t. And I said use the chain rule for the derivative along the parametric path. And the idea is I like to change. I think this is confusing. People always write it this way. But the way to think of it is replace, right, r is a function of a parameter. It's the same curve you sweep out as the parameter sweeps over its domain. I guess here it's probably minus 0 to pi or something like that. So it goes around once, but it could be minus infinity to infinity. Doesn't matter. Um, what I can do is change the parameter. Let's call it u instead of t. Then it takes away a lot of the confusion. So r of u equals 2 sine 2u, 3 cosine 2u. And now what you get is d dt of r of, I said where u equals g of t is, or g of t was t cubed. All right, so I'll rewrite r as a function of u and then say u equals g of t is t cubed. And the idea is we'll just write the usual chain rule and say this is dr, d dt of r of u of t. d dt is dr dt, and you can put canceling du's in here. And then dr du of r is this function of u is then root of sine 2u is 2 cosine 2u, so this becomes twice 2 cosine 2u. And then partial derivative of this one with respect to u, derivative of cosine 2u is minus 2 sine 2u, so I got plus, well, minus 3 times minus 2 sine 2u gives, and then times the UDT, times the UDT is 3t squared. So now I'll rewrite this as 4 cosine 2u, 6 sine 2u, all multiplying 3t squared. Sorry if I'm blocking there. And then put back u equals t cubed. So rewrite this as a function of u and then just write the r du du dt. That's all there is to it. Is 4 cosine 2t cubed times 3t squared, because this multiplies every element. 6 sine 2t cubed times 3t squared. And I've got that simplified. 12t squared cosine 2t cubed, the first element, 18 t squared sine 2t cubed. There it is. I've got another one here for you too. How about this? This isn't on the review, but I might put it on the tab. This was another important concept. So suppose instead of having a derivative of a vector valued function, suppose I have the derivative of a function of a vector valued function like that. Put it on the inside with, suppose f of r of t is x squared plus y squared, right? R being xi plus yj, and r of t is equal to 3, oops, uh, 3 cosine t, 2 sine t. Suppose I had that. This is kind of an interesting problem. I'll mention, in a sense, I'll mention afterward. How do I do that? F is a function of along a curve, r of t. Um, if you go, f of xy is x squared plus y squared, but then x and y are this. This is the idea of the curve. Is this is x and this is y. What we said for that is that df dt could be evaluated using the gradient as gradient of f dot r prime. Right? You're moving along a curve in the plane underneath the surface, right? You got the mountain. It was this picture. You have a path here you're traveling along, and you're actually going along the mountain, but as you move along the path, at any point, what rate are you descending the mountain up here as you move along this path, swept out by R of t? What rate am I descending the mountain? It's this. And you said it's gradient of f dot r prime. So you take gradient of f as the vector 2x, 2y. R prime is the derivative of this one. The derivative of cosine is minus the sine. The derivative of sine is the cosine. And now what you put it back in is x equals 3 cosine t and y equals 2 sine t. You get 6 cosine t when you put x equals 3 cosine t in, and 4 sine t. Got this thing. Gives us, let's see, minus 18 sine t cosine t plus 8 sine t cosine t is minus 10 sine t cosine t when you take the product. Or you might write that as minus 5 sine of 2t using the trig formula. And if I say find the derivative point, you can plug the value t, you can plug t. That's another kind of chain rule. I didn't manage to get it on the review, but it's on the homework I might have. That's a chain rules, right? Great. Okay, well, I'll go ahead and leave it there. Still got half a minute left. Here next time, we'll